So to kick off our functional group chemistry series, we're going to start by looking at alkanes and looking at the reactions that alkanes undergo. But to start off with, let's define what an alkane is by looking at the general formula that we can assign to alkanes. And so the general formula that we assign to alkanes is CnH2n plus 2, where n equals any number. And simply what this means is that for any carbon, any n number of carbons, we're going to have 2 times that number of hydrogens plus an additional 2 hydrogens. And it makes sense. If we have a look at where we have 3 carbons, so n equals 3, of each of these carbons, we're going to have 2 times as many hydrogens. So 1, 2, 3, 4, 5, 6. 6 hydrogens. And so we've dealt with the Cn part of this general formula, and we've dealt with the H2n part of this formula. But we also need to take into account that we've got these additional plus 2 hydrogens. And that makes sense because if we have a look at our carbons, we know that they need to have 4 bonds attached to them, but they only have 3 at the moment. And so those final 2 hydrogens finish us off and satisfy all our rules. And so now our carbon has 4 bonds surrounding it, and so does this one, and same with the central carbon. And additionally, it satisfies our general formula because we have CnH2n plus 2. So we have our n being 3, we've got 3 carbons, and we've got 2 times 3 plus 2, so 8 hydrogens. And so our general formula is CnH2n plus 2. Now, in terms of alkanes, we know that they are saturated, so there are no double bonds between our carbons. So this means that alkanes are generally very unreactive. And once again, this unreactivity is due to only single carbon-carbon bonds. When we talk about alkanes, they're quite reluctant to undergo reactions, but they only undergo 2 types of reactions: combustion reactions and substitution reactions. So let's have a look at the combustion of alkanes. So we already know that when we talk about the combustion of a substance, that water is going to be produced, as well as carbon dioxide, carbon monoxide, or carbon, depending on conditions. And so we know that where we have excess oxygen present as we do our combustion reaction, we're going to have carbon dioxide produced. So that's in excess oxygen. Where we have limited oxygen, we're going to have carbon monoxide produced. And if we have no oxygen, we're going to have just carbon produced. And so that's pretty much as we need to know for our combustion of alkanes. Now remember, we still have one more reaction type to consider, and that's our substitution reactions of alkanes. So let's have a look at our substitution reactions. So in terms of substitution of alkanes, we have quite a complex process that follows. But the first thing we need to know is that our substitution of alkanes takes place when a halogen replaces one of the hydrogens on an alkane. And just to rejog your memory, our halogens are our group 17 elements. So the elements found in group 17, which means all our halogens have 7 outer electrons or valence electrons. And critically, what we need to know is what our halogens are. And so the halogens that we are concerned about are the first 4 in group 17. And so those are fluorine, chlorine, bromine, and iodine. So our first 4 halogens in group 17 are fluorine, chlorine, bromine, and iodine. And so critically, what we need to understand is that our halogens, because they all have 7 outer electrons, they tend to exist diatomically. So let's take bromine for an example. Bromine, because it is in group 17, has 7 outer electrons. 1, 2, 3, 4, 5, 6, 7. And so it still needs to fill up this space because it wants to have 8 outer electrons. And so what bromine will do is pair up with another bromine, which also has 7 outer electrons. 1, 2, 3, 4, 5, 6, 7. And that way they're both satisfied because they share these electrons in order to complete their valency. And so this is the case for most halogens. They exist diatomically for this very reason, because they all have 7 valence electrons. When we're talking about substitution in alkanes, once again, we are replacing a hydrogen for a halogen. And so in order for this to take place, we need our halogen to split up, because remember, they exist diatomically. And so the substitution of alkanes is not as straightforward as we think. It has 3 main phases. And the first phase is initiation. So in initiation, our diatomic halogen needs to be split up. And the mechanism by which this happens is what we call photochemical homolytic fission. And so what happens is our Br2 is zapped with ultraviolet light. And so as a result, our Br2 splits back into its individual Br. So this splits away and this splits away as a result of being exposed to ultraviolet light. And so if we unpack the name of this process, photochemical homolytic fission, we know that photochemical, photo means light, so we've got light involved, specifically ultraviolet light. And this homolytic fission means when our halogen is split, it is split equally. On the other hand, if we had heterolytic fission, what would happen is if we bring our bromine back together, in heterolytic fission, rather than there being an equal split of electrons, one bromine is going to take both of the shared electrons, while the other takes none. So if we see here, we've got one of the bromines took both of the shared electrons, while the other one took none. But what we have instead is homolytic fission, where they both take 1 electron from the shared pair. So our homolytic fission, we can see that this bromine took 1 of the shared electrons and this bromine took the other one. And so homo means same, and so we can see that they split in the same way, receiving the same amount of electrons. Now, we know that atoms usually don't like to exist like this in nature. We've got each bromine having 7 valence electrons rather than 8. And so they are highly, highly reactive in this state. And so now what we have here are these bromine free radicals. And once again, they're free radicals because they have 7 outer electrons and they would like to have 8. And so they are in this highly reactive state where they are willing to react with anything. Now, we indicate that something is a free radical by depicting it like this, with this dot next to it. And so anytime you see that sort of dot next to an element, it means it is a free radical. So that's the initiation phase. What we've done is we've split our halogen, which usually exists diatomically, we've split it with ultraviolet light, and we've split it so that they have the same number of electrons, and so we know that this is called photochemical homolytic fission. So that's step one, the initiation phase. Now we have what we call the propagation phase. So we know that our free radicals are highly reactive, and so in the propagation phase, we're looking at the different reactions that our free radicals are going to undergo as they try to, and so propagation looks at the use and production of free radicals. And so, like we've mentioned, our bromine free radical is highly reactive. And so it's going to pretty much react with whatever it sees. So let's say it encounters methane. What's going to happen is it's going to snatch up one of the hydrogens and take its electron in order to fulfill its valency and get rid of its free radical state. So it's going to become BRH. But because it's taken one of these hydrogens and taken the electron with it, what we're left with is CH3, but this CH3 is a free radical because it's missing an electron. And so this is one example of a propagation reaction. And in theory, propagation reactions can continue pretty much forever. If we react a free radical with a non-free radical, we're going to get rid of one of the free radicals, but we're ultimately going to create a new one. And so here is another example of a free radical propagation reaction. So let's take this new CH3 free radical that we've formed. And let's react that with some bromine. So now what we're going to have is this free radical is going to snatch one of the bromines and take the electrons, and so it's going to be CH3Br, and so this is no longer a free radical because it's taken the electrons from bromine, but in doing so, in splitting up this bromine, it's created a new bromine free radical. And so we can see that propagation is the use and production of free radicals. And like we've already mentioned, this can, in theory, go on forever. This can also be terminated though, and that leads us to our next phase, the termination phase. And so in this phase, we have two free radicals reacting together. And so when these two free radicals react together, it then cancels out the free radicals and we terminate our free radicals. So we get rid of our free radicals. So for example, if we take this free radical here, the CH3 free radical, and join it with this Br free radical, what we're going to end up with is CH3Br. And because we reacted two free radicals together, our product is not going to be a free radical. Whereas if we compare that to our propagation phase, we were reacting free radicals with non-radicals, and so we still ended up forming a free radical in the end. So the key thing to remember is if you react a free radical with a non-free radical, so they are not the same, you're going to still end up with a free radical. Whereas if you react a free radical with another free radical, you will end up terminating the free radical. And so this is the only case in which two wrongs make a right. And so if we come back out, we need to just remember and look at the bigger picture that we're looking at the substitution of alkanes. Now, if we draw out this final product that we have from our termination phase, if we draw that out, we've got CH3 and then Br. But what we started with was CH4. And so we can see here we've had a substitution of our hydrogen for a halogen. And so our substitution reaction has taken place due to these three steps: the initiation phase, which split up our halogen, our propagation phase, in which there was the use and production of free radicals, and then our termination phase, in which two free radicals joined together and gave us our final CH3Br. And so we can see that our fourth H was replaced by a Br. And so that is the process and the mechanism in which a substitution of alkanes by a halogen takes place.